And good morning, everybody. So I'm going to talk about feature decoupling for data analysis. Actually, it's not only for data analysis, but main applications so far have been for data analysis. So when I read the instructions for the workshop or recommendations, they say try to not to go straight to mathematics, but try to spend some time on motivation. So I don't know if I overdid it, but sorry. I have 4 stories for trying to motivate the decoupling. So the first story is about 25 years ago, when I was doing a postdoc with Simon Telly, Center for Neuroscience. We were trying to model in texture. So we end up with quite a successful model. That basically what did was extracting a set of statistical features from the texture. They were homogeneous textures like these ones, and then trying to impose to pseudo-random images. So you can see in these examples that we achieve a good result in general. So it was the first photorealistic model for textures, parametric. So the idea was, as I said, just trying to find, first choosing some good features from the visual point of view that were statistical samples, and then try to impose to a certain random sample these features. There were 2 major problems, though. First of all, we didn't have a good control of the solution. So it was very open, was trying to find a solution, but which solution? And then another problem was these features were not independent of each other. So in practice, what we did was doing some gradient projection that it was moving along the gradient until we impose one of these features. But then when imposing one feature, we spoil the other ones a little bit because they were not independent. So another classical method that was not chosen because it was more complicated was doing orthogonal projections. Somehow orthogonal projection and gradient projection are dual. So if you go reverse, orthogonal projection is like going forward gradient projection and vice versa. But we see that this is not a good way to do things because it's not reversible. So you're losing information. Instead of that, if you go all the way going orthogonal to the iso surfaces, you can do reverse, right? Like finding the solution of an ordinary differential equation. And this is what I'm proposing here. Also, from a statistical point of view, you cannot model the density of the transformed image unless you have a defined transformation, controlled transformation of your variable, in this case, the image. So going to this mathematical incompatible thing, so we can think about some simple examples like standardized moments, like skewness, kurtosis. When I'm talking about the statistics, I'm meaning actually sample statistics, right? So there are deterministic functions that estimate the statistics. So what happens in practice, this of course depends on the number of samples, is that when you have a very high skewness, you cannot have a low kurtosis. They are incompatible. So there is a dependency that, and that is a key point. This boundary, the shape of these compatible regions does not depend on the statistics of the input. Does not depend. It's an algebraic constraint, right? It's a hard algebraic constraint. So I'm not going to talk here about decoupling in a statistical sense, but decoupling in a deterministic sense, because it refers to the algebraic features, right? This is another example. If we have the sample of the covariance in 1D, of course, we cannot have autocovariance with the immediate neighbor 1. That means they are doing the same thing. And then the second one, 0. It's impossible. They are coupled, right? So you get things like that, these regions of compatibility. So there is an interesting consequence for people trying to do simulation, creating signals or images that look like real, is that you cannot have knobs and change something without changing the other ones, right? So unless you decouple your features, if you change one feature, the other knobs will move along. So then you will try to adjust the knobs in an iterative way. This is what we did in 2000, right? So I had this motivation for doing this for many years, and finally, like 6 years ago, 7 years ago, I found a possible way. That is what I'm going to say here. The second story is just a more qualitative reflection on how our brain and our sensory system, particularly vision, works. Imagine that we have two features. This is very naive, but I hope it expresses the idea. The two features here would be the total size and the head size. And we have some schematic possible human beings that are very simple, but have different size, total size, and different head size. Of course, these two features are coupled, right? Because if we go along the gradient of the total size, we will affect the head size. Interestingly, if we observe, I cannot occlude here, but imagine I should have done it better. I occlude one of these drawings and ask you how big is the head, and then I occlude the other one. I ask how big is the head, and probably many people would say it's larger, the one on the left, but they are the same, right? Why is this? Because our sensory and our high level also semantics tends to normalize. So we are not so focused on absolute values because they change on the observation conditions, but on relative observations. So the conjecture is there like a kind of a universal mechanism for normalizing in our brain? This is very qualitative, so don't take it too concrete, but more like a general concept. A third story that may be more close to mathematician approach is about the moments. Why we standardize moments? Why it's interesting to talk about variance instead of mean square value? Why we subtract the mean and we to estimate the variance? Why we divide by the square root of the variance to standardize, right? Why subtract? Why divide? So we say, yeah, it works, makes sense. So what I propose here is a general approach explaining why is that precisely, and try to go further. So what happens with the next standardized moment, that is the kurtosis? Kurtosis and skewness, as I have shown before, they are not decoupled, right? So what should we do? What should we do with kurtosis to enforce this decoupling behavior? And the fourth story is related to more to my research field in general, that is images and vision. So we can think about the images carrying two types of information. First is the appearance, that is the type of style of the image, maybe the quality. It has more texture, it has less texture, it's blurry, not blurry. Maybe the distribution of the colors. The other one is the semantics. That is what typically machine learning or deep learning algorithms try to interpret. Sorry. Just want to know the time and it gets vanishing, sorry. So what about trying to, these informations are not completely separated, they do intersect. For instance, when we look at the sunset, the light is, the dominant light may be red, and this is giving us information about the semantics, right? But typically we can change a lot of things in the images without affecting the interpretation of what's going on in the image, right? We can change high frequencies. Yesterday we saw some examples. We can change texture, we can change color, and we still see the meaning, what's going on in the image, right? So this is telling us there are some invariants. Maybe I'm advancing a mathematical term that is not always correct, but invariance of manifolds. We can move through these invariant manifolds without affecting or not seriously affecting the semantics. So it could be something like that. We can think about images like a vector, Euclidean space, maybe. But instead of thinking, okay, we have some orthogonal coordinates that are the pixels, we have some curved nonlinear coordinates involving the whole image that are the style or describing the style, and then other non-redundant coordinates that are more related to the local structures appearing in the image, right? So this is an example of something that we'll talk a little bit more later on. We can do style transfer if we are able to separate these things in a very literal way. So we just take the things that is like onion layers. We take the external onion layers, describing, in this case, they are describing the first order statistics of the luminance and second order statistics of chrominance, color in a certain representation. And this is a real example. Okay. If there is something that you don't understand and it's not clear, please interrupt. So let's go to the math. We are focusing on features that have this expression. So they can be like sample statistics. We are averaging in the whole image some features, local features, right? So we define that two features are decoupled on a certain domain D if their gradients are orthogonal everywhere on that domain. So you can see that this is very different to what some people think when you say decoupling. They think about principal component analysis or some statistical transformations, right? This is a purely algebraic concept. So our goal is giving a set of non-trivially, I'm not going to define what is non-trivially, but is intuitive. Yeah. Yes. Sure. So we have a set of features that are global features having this structure, could be sample statistics. And our goal is to find these features accomplishing this, right? Okay. Okay. So this is our goal. More precisely, we are going to define some high dimensional manifolds, when we say we have a given set that they don't accomplish this, in general, it is the case. And we want to accomplish this decoupling feature. What we try is to have a very high dimensional manifold within which the new features are exactly the same as the old ones, right? And there is another high dimensional manifold where they exactly accomplish the orthogonality. Of course, the ideal case is that this high dimensional manifold is the whole space. In some cases we achieve it, in some cases not, right? Okay, so here's the central idea. If you understand this, you'll say, okay. And you'll say, well, it's so simple. It's so simple. I hope not deceptively simple. So here's the simplest case, of course, is when we start with a single feature and see how we can construct another feature whose gradients are orthogonal to the first feature, okay? So we are in a Euclidean space, we have a vector, and we have a gradient system. We have a feature that is F1, and we say, okay, we get these manifolds, submanifolds, just moving along the gradient, classical. And next component is say, okay, we are moving along, in this case, along this line. And when we stop, we are stopping when we get a certain value for the function. This is what we have called the goal manifold or reference manifold. So we fix or prefix a reference value for forcing the feature, the first feature, to have this one when moving along this, right? Is clear this? So look, all these intermediate values, vectors, are going to the same place. This means that all the vectors in this manifold are going to have this same normalization. Clear so far? Then we define the decoupled feature as a differentiable function of this normalized vector. Because all the vectors within this submanifold have the same normalized, they go to the same vector, then all of them will have this F2 invert hat value, the same value, because they go to the same place, right? So that means that these submanifolds are iso F2 hat value, right? They go to the same place. Because of that, then their gradient is orthogonal to this manifold. Is clear the idea? It takes a while to assimilate. No, in the one-dimensional case, no. In the higher dimensional case, yes. In the one-dimensional case, you just move along the gradient. I mean, there are some basic features you need to require, like non-pathological, differentiable, and maybe some other. This is in the paper, the technicalities. You just move along the gradient. In this case, you just have one gradient. I'm going to talk about having more features, and then you have more than one gradient, and then you have more degrees of freedom. Yeah, exactly. Okay. So that's good question, because it helps me to introduce the case where you have more than one feature and you want to fix at the same time several values. Then you have more degrees of freedom because you have several gradients. If you're lucky, you have a manifold. Not always, of course. It depends. So locally, there is I'm advancing something that comes later on. There's a theorem from Frobenius telling you in which cases you have integrable manifold from some vector fields. In this case, the vector fields are the gradients, right? So the interesting thing is you have this invariance manifold that you can move along, okay? And the tangent plane is done by the linear combination of your gradients. So now, if this manifold, invariance manifold exists, and this is the big thing, the big if is in red, then any differentiable function, gx, fulfills that this new function is decoupled to every feature in S, to everyone. When I say that it's decoupled to a set of features, it's decoupled to every feature in the set. That's the important thing. And we can write in a more general way our normalized solution as the reference manifold. This is this manifold exists if F behaves normally, right? So as the intersection of this. There are some conditions. Where are the conditions? Oh, sorry, I'm going in the there are some conditions that must be held. Some of them are quite stringent, like not having non-global extrema. This is important. So every maximum or minimum of these features should be absolute maximum, absolute minimum. This is quite stringent, but it happens. It is still applies to many of these features that are global, that do averages. Of course, absence of critical points. And this is a tricky aspect, low dimensionality of the basins of attraction of the saddles. Otherwise, you can get stuck, right? Watch out digital data. When one says, okay, low dimensional, the probability is 0 because the Levesque measure is 0, but it's not because you have digital data. So they concentrate to certain values. So how to solve this is not a big deal. You just need to add a perturbation, a small perturbation. So if all these things hold, then you have that the normalization exists and is unique. Just removing this subspace of basin attraction of the solids. Okay. So this is interesting because it's more open than the previous graph. So now you can follow whatever ordinary differential equation trajectories you want. You can choose. There are many possibilities to arrive from one point to another one, in this case to the reference manifold. And because it's unique, doesn't matter. This looks like a little bit like a conservative fields in physics. So it doesn't matter how you go, you get to the same potential. So it's very similar. And this is important in practice for finding solutions, convenient solutions. But we can also follow more restricted sequential integration path that we call it nested normalizations. That is doing like a very simple, very constrained path that you follow one gradient every time. So you follow the gradient of feature 1 until you arrive to the reference value for F1. Then you follow the projected gradient of F2 until reaching the reference value, and so on. This implies an hierarchy between these features. That may be natural, for instance, for the moments, the same as we have the standardized moments. May be natural for other situations, but may not be natural for others. So it's not always a good thing to do things hierarchically. But well, the good thing is because everything is reversible, there are no singularities, there are not pits we fall into. We can go and reverse things, right? So we can go transform our image, impose every time a reference value for this structure of these onion layers. And then we can either go back, and will be completely reversible as long as we have saved these values that we have obtained, the orthogonal features. Or we can impose other features. And this is the way we did with the style transfer, right? So you get a kernel, and then it's like dressing one of these, this paper, what's it called? Muñecos, what is it? No me sabe la palabra. And there are this minimalistic toy that is having a paper drawing of someone, and then you put some dressing on it, no? And you change. So this is like changing the dressing. Oh, sorry for a sloppy explanation. So study cases. So very easy cases are like marginal moments. We'll go to the next one. They accomplish the Frobenius condition, so they define a manifold. Also the autocorrelation, that's matter 1D or 2D. Interesting thing is to measure the moments at the output of a set of filters and for images. And this doesn't accomplish Frobenius, only for the variance. When we measure the variance at the output of some filters, they do, but in other for other exponents, for other powers, though. But this is interesting because even if they don't accomplish Frobenius, it works reasonably well, as I will show. Okay, this is just some things about implementation. Okay, so about the orthokurtosis, I'm not going to give the details of the orthokurtosis because it's a little bit long, but it's just following this approach. And just to give an impression of how does it look, the orthokurtosis, right? This could be the skewness depicted in a actually it's a 4-dimensional space, but we constrain to be on the sphere. So it looks like 3-dimensional. It's more than that. So you may think, oh, of course it's a sphere. So there is another, okay, this is zero mean. The zero mean constraint helps the 4-dimensional case to go to a single sphere. And this is how it looks, the kurtosis and the skewness. And you see that the peaks, absolute peaks of the skewness are located at the absolute peaks of the kurtosis. And here's the orthokurtosis, how it looks like. There's a singularity here, okay. So applications, that's really make a difference when applying. First of all, checking if this really orthogonalizes the gradients. So we just did some experiments, not going to get into the details, but this was just sample moments, right? Here we use from 1st to 6th order, and we compute the angle between the gradients and compute the mean of this difference to the orthogonal angle and the standard deviation. And then we did this with the normal moments and then with the orthogonal moments. So here's the normal moments, and this is the orthogonal moments. This is for random Gaussian samples. And up to the 4th order moment is exact, and then it's very approximate, as you can see here. Then we did that for real images, for texture patches, and then now it's not so perfect, but it's much better than just using the. This is the first 3 ones are perfectly decoupled because they were using the standardized moment, so were mean, variance, and standardized. But then from the 3rd on, they were coupled, right? Applications. So there is a very interesting property of the ortho features is that locally they decorrelate. When you have a function of this that is going in the expectation is going to converge to the statistics. We demonstrate that locally it decorrelates perfectly every if the gradients are orthogonal in the limit, having many samples, it decorrelates completely the two features in a statistical sense now. So it is very important because this is in the limit and under local conditions is converging. This algebraic decoupling and this statistical decoupling are converging. That's very important. You can see here a real example with samples that are 1,024 samples of artificially generated, pseudo-random. Is a Gaussian up to a certain power. So you can see that skewness and kurtosis are extremely correlated, and they overlap along the direction of this correlation. Because we break this correlation, here we had a 12% error using a Gaussian model. And here we have a 4% error. Okay, going to real textures. The problem is that we have some small patches and we want to decide to which texture belong. So we use a set of filters, a tight frame, and we use several moments at the output of those filters, even if they no longer accomplish the theoretical condition of to build real manifolds, submanifolds, but still they work. So we remember this constraint of skewness and kurtosis. We can see this here. This is skewness, this is kurtosis. We have this dependency. This is skewness and fifth order, kurtosis fifth order, and this is after the decoupling, right? And this is for these two textures. And so it works very well. In blue is our results with decoupling. In dot line is naive Bayesian, naive Bayes, and in continuous line is super vector machine, right? So we can go down to even the 10th, which usually is not. These higher moments are very unstable and they're not useful. We can go really down, and every time we add a little bit, actually until 6 probably is enough, right? But we can get a very big improvement over classical moments. Another thing that is interesting, we can not only apply this decoupling of moments independently to every subband, to every filter in the tight frame. But we can also apply, following this nested normalization scheme, just invent an arbitrary order between the features and between the different filters also do decoupling. So this is what we call here fully decoupled. And we can see it improves quite a lot, right? So even that's a very interesting thing, even using an extremely simple method like naive Bayes, because naive Bayes is assuming things are independent, and now they are close to independent. Now it works almost as well as using a sophisticated method like super vector machine. That's very interesting. This is just remembering that it's not holding the theory, but it still is approximating very well. Okay, we apply this also to regression. I'm going to go a little bit faster. Just different PDF densities. So here is a skew normal. It has a shape parameter. So we want to estimate the shape parameter. And this is the red one that is much more concentrated, is the location of the samples in the space of the skewness, kurtosis, and shape parameter. And this is using the standard moments. So it's much more concentrated. It means that we are getting less uncertainty, more information about the parameter we want to estimate. And so we get better results, much better results, like less than half error. Another example, and this is the result, the root mean square error. And there's yet another one. Okay. Just to finish, okay, before finishing, we can apply this to transform images in a reversible way, as I said before. So now we have actually implemented this. This is an actual implementation in MATLAB with a graphical user interface. So we have some knobs, and now instead of having kurtosis, we have orthokurtosis, and we can change these things. And the interesting thing is that if we go back to the previous one, we have, this is 120 dB, so we are recovering exactly the same image. So we are not losing information, right? The same thing we can apply to textures. For now, the models for texture are very simple because we wanted to then to comply with the Frobenius condition. So this is an example, and then this is an example of navigating in the parameter space, because now there are no forbidden combinations. You can just move whatever combination you want, right? I have talked about before about the style transfer. This is joint work with Marcelo Bertalmino. And just the last one I want to talk about quickly is from normalization to optimization. Try to make this a more flexible approach. So we have talked about this navigating within the invariance of manifolds until reaching some reference values. But why just stopping in reference values? We can do other things. We could do things like doing averages if you will have a density, or we could optimize a function, right? And this is what we have done lately. We have chosen a cost function that is meaningful visually, that is telling us if we reduce this cost function, we will see better the image. And we try to optimize it. And as long as this implies getting a single value for each submanifold, we will get the same property of decoupling, right? So the last work we have presented recently in Lyon, in France, is using this for improving the image when we have the problem of analyzing images from out of distribution images. So the thing is that we have, in our case, very blurred image. By the way, these are real examples. And what it happens is that the low level features don't have enough contrast to trigger the recognition, right? And here we apply our ortho feature approach to the variance of the output of some filters. So we optimize the variance for making the image more visible according to a criterion that was entropic information, right? Recovering as much information as possible. And this triggered recognition. This is a real example. And this is another real example. And that is interesting. So this is the latent image, so perfect one. And the simulated observation is very blurred. It thinks like it's a cat. Then we apply off-the-shelf image processing method, Bayesian, classical, based on sparsity. And the problem is that, yeah, it looks nicer. It has sharper edges, but it has destroyed a lot of texture. Not very good, right? The solution is one of these, the Greek one, I think. These ones were non-blind, and these are blind. The blind ones, they do very bad, right? And we are this blue one. So the interesting thing is that the image that helps to get better analysis results is not necessarily the one that looks nice. This is a dramatic silence for people to try to assimilate, because this is a very important conclusion, right? We don't want things to look good. We want things to be informative for the network, for the artificial network, or also for our vision. And we are also, okay, I'm finishing. Well, this is a very redundant thing, but basically, it is very important to look at the statistics of features, not just because of being generated by the statistics of the input, but because of being generated from the joint algebraic structure of the features, right? It's a very important thing. These are some references, and so now acknowledgement. I have done this with, she's a mathematician, and some engineers, mathematicians, or many people that have helped to do this. So thank you very much.
Okay, we have time for some questions.
You means image contain two type of information, surf appearance and semantic.
Yes.
And in your work, you mainly focus on appearance. Is the semantic part touched or not touched?
Right. So we focus on changing the appearance, because this hopefully will not affect to the semantic content of the image.
Okay.
Yeah, it's the degree of freedom we have, maybe for adapting to the preferred range of the analysis system, right? We have this degree of freedom.
Okay.
Try not to change the semantics. Yeah.
How does it compare with the feature decoupling of adversarial networks and the kind?
I haven't made this comparison. For the case of adversarial networks, I'm not familiar of the decoupling properties, so I cannot answer. But so far, what I can tell is that I have tried to make a very thorough search for. Of course, I was very afraid of this already being known, and so far I haven't found it. But I would appreciate very much if you can send me a pointer if there is a connection. Meaningful connection.
I have seen some like latent space on adversarial networks where you have kind
Yes.
of orthogonal, for example, for faces, they could
Right.
separate larger ears,
Yes,
bigger
yes.
nose. So
it has some
seems to work.
parallelism with the latent space of neural networks, in the sense that you can move without problems in that space, instead of the space of the features of the simple features. But the good thing about this, which is complementary, it's not better, it's just complementary, is that is based on explicit algebraic expressions, right? So it's not a black box. You can understand, although you can also understand the qualitative principles for doing this latent space. And it's also very interesting for describing the vision, right? Human vision. Like this, you are with your feet on the mathematical ground, which has some advantages, right? I'm not saying it's better, it's different, right?
And do you think you can fix there something that is not completely orthogonal, but somehow coupled?
Actually, we get the results. We have an intermediate result, is that when some conditions hold but not others, we can define some high dimensional manifolds where they are exactly orthogonal. If you choose well your reference value, these may be the most likely values, right? The most likely, for instance, for density, you get the most likely moments, values for the moments, then you will not be too far from there. So that you will be close to orthogonal. This is why we wanted to empirically test the actual orthogonality. Yeah.
Any other questions?
A short question. Your texture classification is an unsupervised process or a supervised. So there is a taxonomy of texture, or there's no such kind of thing, just clustering.
If you mean the model for synthesizing texture, or
target Do you have a taxonomy?
Yeah.
of textures?
You have is completely supervised. You say,
Supervised.
yeah, you have some appearance that you want to transfer to your sample. So you are telling which values. I don't know if this is what you are asking.
How many
How
texture
many
classes do you have?
How many parameters?
Texture classes.
Oh,
Class of text.
in this case, I think we're 60 or 80. I don't remember.
80.
Something like that. Yeah,
Okay.
in that order.
Okay, let's
No,
thank the speaker.
There's another one.
Thank you for the talk. How do you choose the reference values? Can you talk a bit about that?
Yeah, that's related to what I was saying before. Especially for the cases that you don't achieve exact orthogonality, it is convenient to choose likely values, right? So from a statistical point of view, you want to have typical samples, right? So you have a sample that is not very typical, you make it more typical, right? But the interesting thing is that it's similar to the what you do with standardized moments. You apply zero mean, unit variance. This is just imposing it. But of course, you can adapt the mean. That doesn't matter the actual value, right? You can just rescale and move your data. So to have zero mean standard. So it's similar. And if you want to improve the image, you do something a little bit better that is not just a reference, but an optimal value, right? Then you include this optimization stage that we basically try to increase the entropy. So basically was trying to amplify the channels, the spectral channels, as much as possible without getting out of the range.